Welcome back, everyone. Let's keep on building applications and examples of vector differentiation, specifically the differentiation of a vector valued function of a single variable. So what we have here is a specific example. It's a pretty interesting one as well. It's one which we'll have to use over and over again. So it's not just an example, it's a very important lesson for us that we'll need to memorize in order to be better at applying the concept of vector differentiation. So what does it say? It says that a curve C is defined by, and there are three equations: x equal to x of s, that means x as a function of s, y as a function of s, and z as a function of s. So from this statement, what we understand is that it is defined in terms of the coordinates, and the coordinates are parametrized. That means the curve itself is parametrized with respect to s. And this is consistent with what we have seen before. If a curve is parametrized by a parameter, let's say s or time, or any arbitrary parameter u, then the coordinate functions will be functions of those parameters, the coordinate functions that define the curve under study. So that's exactly what we see. Now here, of course, we have chosen a specific parameter, which is the parameter s, which is the arc length. So let me talk a little bit about this specific parameterization. So we have s is the arc length parameterization. So what does it mean? It means if you take any point, well, you take a point, so let's say this is the point P, and this is the curve C. So basically s is the distance of the point under study. Let's say the point is Q. Now the point P has to be regarded as a fixed point, so this is fixed, okay? And the point Q is a function of s, because as you move, as you change the value of x, the point Q changes its position. So that means the distance s is always being measured from the fixed point P that lives on the curve C. As you change the value of s, you go from one point to another point, so you go along the curve C. Well, that is the goal of parameterization. Let me bring it here. Alright. And r is the position vector, which in turn will also be a function of the parameter, and r is the position vector that traces out the curve C. So that means here you have a coordinate system, and r is a position vector, so it goes from here to there. And of course, just like q, r will also be a function of s. So r is the position vector that changes along with the point q. Okay, so it, as s changes, r traces out the curve C. Now this r is, of course, can be explicitly written as x of s times x hat plus y of s times y hat plus z of s times z hat. Alright. Now you can take dr. That means you simply take the differential of each of the coordinate functions. So you have dx x hat plus dy y hat plus ds dz z hat. We could have started with delta r, so the finite difference between the position vectors of two different points of the curve, and then we could have taken the limits we would have derived here. But since this point is intuitively straightforward, we just write down the differential identity at once, and from this we can find out dr, its magnitude, is simply according to the rule of vectors, dx whole squared plus dy whole squared plus dz whole squared. I do understand that this process will bring out criticisms from mathematicians, but I think this point is intuitive enough and rigorous enough, so we just simply go ahead with this. By the way, this is exactly what we define by the arc length, so ds, or rather square root of ds squared, okay? And that's pretty much it. This can be written as ds. Once you do that, what you can get is that the r ds, so the derivative of r, the position vector with respect to s, and presumably so you should get dx of s ds x hat plus dy of s over ds y hat. We're simply differentiating the r vector with respect to the parametrization, so dz of s over ds and then z hat. Alright, and then you take the magnitude of this thing here, so dr over ds. Okay, and what does that give us? That gives us dx over ds all squared. Okay, plus similarly all the components squared and then summed over, and then of course there is a square root has to be put over it, so over half. Now of course these are ordinary derivatives, and therefore we know they act as a, well, not the whole thing, but the differentials, they act like separate entities. So these things can be dealt like fractions, even though technically they're not exactly fractions, but nonetheless we can write the following statement. I'm hoping not to incur someone else's wrath upon me. This would be dx squared plus dy squared plus dz squared. I'm dropping the parentheses, but what we can immediately see is that the quantity on the top is exactly what we have written as ds squared. So basically this ends up as 1. So there we go. We have proven exactly what we set out to prove. It's not a very difficult proof, but nonetheless it's a necessary one. When you find out the derivative of the position vector with respect to any parametrization, it gives you a tangent vector. So the vector is tangent, there's no doubt about it, but now we have proven that this tangent vector is also a unit vector. When you have a unit tangent vector, it is typically denoted by a capital T, or at least will continue to do so, as you'll see in the future videos. And by the way, even though this is a unit vector, this is not a constant vector, it still depends on S. So by construction, this T is found when you differentiate the position vector with respect to the arc length parametrization, and it is by construction a unit tangent vector. So that is the first application we set out to do. Another application we'll be seeing would be like proving an identity. So this would be the identity we are set out to prove next. What this tells us is that a vector valued function of a single variable, a of t. So a is the vector valued function and t is the single scalar variable. A of t dotted with its derivative, okay, is the same as the magnitude of a of t dotted with the magnitude of the derivative of a of t. Okay. This is a very interesting result, and this is a very important one as well. And we're going to prove it. There are two ways to show that. Of course, one is the straightforward way. You just deal them as vectors. And the other way is to introduce a coordinate system and to prove this in a coordinate system. And both are valid proofs, by the way. One is just a bit longer than the other one, but one can also argue that proving things in coordinates sometimes simplifies things a lot. I think it boils down to a matter of choice and taste, but we're going to show both of them anyway. So let's show the long one first. Let's write A in a coordinate system. So you have ax x hat plus ay y hat plus az z hat. Of course, a x, ay, az are all functions of t, so they inherit the parametrization from the original vector. And of course, the magnitude of A is simply the sum of the squares. So ax squared plus ay squared plus az squared with an overall square root. Okay. And you can just by brute force differentiate the magnitude. So you have dA over dt. So what will happen is that you'll use the chain rule. So if you differentiate the square root, you're going to have 1 over 2 times the square root itself as it happens. So you're supposed to get 1 over 2 square root of a1 squared plus a2 squared plus a3 squared. Okay, so I guess I could have just written a here, and then in the inside you haven't got t, you have got another bunch of functions that you have to differentiate again. So if you differentiate ax squared, you get twice ax and the derivative of ax with respect to t. You see, the chain rule. The same thing happens over and over again. So twice ay, derivative of ay, twice az, differentiation of az, and that's it. One thing we could have done is to take this 2 and then divide all the 2's overall. So what will happen is that the 2's will cancel themselves, and then the rest of the quantity in the parenthesis looks like a dot product, right? It's the dot product of 2 vectors, so you get the x component of the first vector dotted multiplied with the x component of the second vector plus y component of the first vector multiplied with the y component of the second vector, and so on and so forth. So it definitely looks like a dot product, and it can be written in fact as a dot product. So the quantity on the bottom, we simply can write it as 1 over a, and here you can just simply take this quantity and write a dotted with the derivative of a, and then send the a on the bottom to the other side. So you have a times dA over dt equals a dotted with dA over dt, and that was our goal. Now another way we could have gone is to take the dot product first, right? A dot a, which is simply a squared, and then simply take the derivative. So if you take the derivative on both sides, well, I could just put it here, can't I? Right, and on the right hand side I can write ddt. Okay, that's great. So what will happen is on the left hand side you have got a dotted with dA dt, and then of course plus you take the derivative of the leftover vector, but it's essentially the same thing, isn't it? Because the dot product is symmetric. Okay, so it doesn't matter whether you write the vector a first or the derivative first. And on the right hand side you have got 2 times a times dA dt. So in both of these sides you have found twice a dotted with dA dt, both are vectors, and on the right side you have got twice a dA dt, both are scalars, just the magnitudes of two different vectors. And that's it. You just cancel the 2's from both sides, and you have found what you set out to derive. And so this is just simply another simple way to approach it. One thing you should be aware of is that if a is a constant, right, you will get the right hand side to be 0. So the right hand side is 0 if the magnitude of a, right, is constant. So that means for a constant vector, the vector and its derivative are both perpendicular on each other, right? Because the magnitude is constant, it doesn't mean that you cannot take the derivative of the vector, because a constant vector, right, can still be parametrized. So if I know that this vector, its magnitude is constant, but still it is parametrized, that means yes, the magnitude, this one is constant, but the unit vector, let's say u hat, this then carries the parameter. This is consistent with an example we have seen in a previous video. So if you're watching the whole playlist, then it should simply be natural to you and also familiar to you. And this is how you can see different things from the same thing from different perspectives. Now let's move on and go for another application. This time we take refuge in physics. Alright, so this is the problem we'll be dealing with now. This problem talks about a particle, so a particle that moves, and its movement is described by this position vector cosine of omega t x hat plus sine of omega t y hat, where omega is a constant. Alright, those who study physics can promptly understand that omega is what we call the angular speed, but we'll talk about that later. What we'll have to show is a couple of things. First of all, the velocity is perpendicular to the position vector, and there's no mention of a specific time, so that means it keeps being perpendicular on the position vector at all time, as long as the motion or the position of the particle is defined by this r here. Then the acceleration is directed toward the origin, and the acceleration is proportional to the distance from the origin. The magnitude of the acceleration is proportional to the distance from the origin, and r cross v. So here's a cross product. Of course, these are perpendicular, so I guess taking the cross product should be easier in the sense that it is guaranteed to be non-zero. But now we'll have to show that this r cross v is a constant vector. That means it doesn't change with time. I think the questions are simple enough, so without further ado, it is time that we go on to solve this problem. So the first one should be much straightforward. First we need to calculate the velocity, which is simply dr over dt. And this is going to be, so omega cosine omega t when differentiated gives us negative omega sine of omega t times x hat. And when sine omega t is differentiated, then omega comes out and it becomes cosine of omega t times y hat. Now we'll simply have to calculate the dot product v dot r, okay, or r dot v. And if they are perpendicular, then of course what we should get as a result is 0. because two vectors which are orthogonal to each other or perpendicular to each other have 0 dot product. So negative omega sine of omega t, so that's the x component of v, times the x component of r, which would be cosine of omega t, plus you have omega cosine of omega t times sine of omega t. Now you can immediately see these two are the same quantity, except for they have opposite signs. One has a positive sign and the other has a negative sign, so they cancel each other, so you get 0, which means that v and r are in fact orthogonal or perpendicular to each other. So that is the first one. The next one is where we'll have to calculate the acceleration. So we already have the velocity. Let's just differentiate it and we'll get the acceleration. So if you differentiate the velocity, this would be a, and this is equal to negative omega. Then when you differentiate sine omega t, you should get another omega out, so omega squared. Sine turns to cosine of omega t times x hat, and then plus you have omega, another omega comes out, so omega squared. Cosine becomes negative sine, so we should actually put on a negative sign here, and then cosine becomes sine of omega t times y hat, right? And now you can factor out this negative omega squared, and you're left with cosine of omega t times x hat plus sine sine of omega t times y hat. And notice this is nothing but the position vector. The one in the parenthesis is simply the position vector. And what does it signify? So omega is a constant, so that means this acceleration is proportional to the position vector, but with a negative sign. That means it's opposite to the position vector, so that means if the particle is here, this would be the r, okay, and this would be the acceleration vector. Well, it doesn't have to be that long, so it just have to be opposite to the position vector, and that is the direction toward the origin. Okay. In addition, you can also see if I take the magnitude, right? The magnitude of A is written as just A, you get omega times R, right? Or we can just simply explicitly write it, which is the absolute value of negative omega, and then the magnitude of R, so this is omega R. So as you can see, A is indeed proportional to R, the distance from the origin to the particle. There should be a square somewhere, right? Oh, here it is. Here is a square, here is a square, here is a square, and there you go. So, yeah, small mistake, but better not to make any. So A equal to omega squared R. By the way, the acceleration vector, any acceleration vector that can be written as negative omega squared R, the position vector, this is by definition what we call the centripetal acceleration. Centripetal acceleration. And this has a distinct physical meaning. Centripetal acceleration is when you can see a particle moving at a constant velocity around a circle. I'm sorry, a constant speed around a circle, because if you go around a circle, the velocity by definition isn't constant. So any particle that goes around at a constant speed around a circle will follow this equation of motion. So its equation of motion is going to be negative omega acceleration equal to negative omega squared R, and that is the physical meaning. So that concludes the solution to number B. Let's move on to number C, where we'll have to find out the cross product between the position vector and the velocity vector, and we'll have to show that this is supposed to be constant. So these are the two vectors of which we'll have to take the cross products. So R cross V. This is number C, of course, we are trying. And this shouldn't be very difficult because both of these vectors have only two components. Both are missing the z component. So x hat, y hat, z hat, or z hat, depends on where you are from and your preference. In place of r, you have cosine of omega t, then sine of omega t, and in for the coefficient of z you have 0. Similarly, here you have negative omega sine of omega t and omega cosine of omega t for the y component, and again 0 for the z component. And this is pretty straightforward, right? Because if you take x hat, its coefficient is going to be sine omega t times 0 minus omega cosine omega t times 0, so that's 0. Similarly, the component of y will also end up being 0, right? You go like that, so that multiplication also yields 0, and so does this one. So you don't have any component regarding or involving x hat and y hat, so the only surviving component would be that of z hat. So the coefficient of z hat is going to be cosine squared, so omega times cosine squared omega t, and then you have a minus sign, and you have to put a minus sign due to the rule of the determinant, and then you have omega sine squared omega t, and well, two minus signs make it a plus, right? Because you know the rule dictates a minus sign, and you have an extra minus sign here. So you can just simply take out omega and then z hat. You factored out omega, but notice if you factor out omega, you simply get cosine squared plus sine squared, which is simply 1. So this is what we have left. This is the result, and omega is a constant. And remember, the Cartesian coordinate z hat is also a constant, so the whole thing is a constant vector. And this is another property of the constant circular motion. Alright, and this particular property, that r cross v is going to be a constant vector, is involved with what we call the conservation of angular momentum. Okay, because angular momentum in this case would be r cross p. P is the linear momentum, which is mv for a particle, and this simply means that the angular momentum, which is written as L, is m times omega z hat, and this is constant, which is an amazing result for us, because in physics, anytime you get a constant of motion is good for you. The motion in that degree of freedom particularly is simple to state and use. In the next video, we shall be talking about the partial derivative of a vector valued function. So that means the vector valued function now has, instead of a single variable, a number of variables, more than one variables, and so in order to differentiate that, we'll have to consider partial derivative of vectors. See you on the next video. Bye bye.